Our next talk is on security bounds for proof carrying data from straight line extractors, and Z will give the talk.
Hello again. Thank you for the introduction. And this is joint work with Ale, Shaha, and Elon. Yeah, they are definitely amazing. It was like already mentioned yesterday. So before I go into like an infinite series of definitions, I want to first provide a roadmap. So when you like enjoy the business meeting, whatever this is, you at least remember something from this session. So I'm going to talk about proof carrying data. And it's essentially a recursive composition of snarks. And we've seen snarks like 20 times today. And recursion is also reasonable, so we know what it is. And it's been very useful for efficiently verifying distributed computations. But there is one issue. In practice, people actually deploy PCD schemes under the assumption that the PCD is as secure as the underlying snarks, regardless of how many recursions that you do. But this is actually not proven. So existing constructions, existing security analysis, they actually show that there is a huge gap between the security of PCD and its underlying snarks. So in this work, what we do is that we propose a new idealization of hash-based PCD in the random oracle model. And we show that for this idealized PCD, it's actually as secure as the underlying snark. And this actually provides the first justification of what people do in practice. So now, definitions. What's proof carrying data? As mentioned before, it's very useful for efficiently verifiable distributed computations. And let's see a very simple examples. I want to sum 6 numbers, and I have 6 distributed pandas. And I ask each of them to compute the sum of one number and give me a proof. And then I find a way to aggregate the proof until I have the sum of the 6 numbers and a corresponding proof that can help me to verify that the computation is actually correct. So now, like with that very cute example, we can actually model PCD construction in terms of a tree-like transcript. And in this case, in this slide, I just give an example of a PCD transcript with size h and depth 3. And what we need for this PCD transcript is that we want to use the transcript to somehow tell us that the computation underlying this PCD computation is correct. And this is captured by this very amazing function phi, which we call the compliance predicate of the computation. And it takes in necessary information about the highlighted node. And we say that the node, the blue one, is correct if the predicate accepts. And moreover, we require that the accompanying proof for this particular node to be able to show us first that the target node is correct, and also that every single child vertices has correct computation. And then with this abstraction, we're able to define the interface of the PCD prover and verifier, which give us a proof system. And as every other proof system, we have security guarantee. And in this case, we are particularly interested about the knowledge soundness of the PCD scheme. And roughly speaking, it's saying that consider a malicious prover, an adversary, that chooses a particular computation captured by this predicate phi, an output of the computation, and a final proof. In the case that the prover successfully convinces the verifier, the prover must know some compliance transcript that is correct. And in other words, the probability that the prover convinces the verifier, but no extractor can extract a correct transcript, is upper bounded by some small number kappa. And as mentioned before, PCD is literally just recursive composition of snarks. Although we've seen snarks for 100 times, I still want to mention the basic interface for snark and for a particular NP-complete language, our favorite one, circuit set. We have the prover, the verifier, and we also have knowledge soundness, which is saying that in the case that the adversary convinces the verifier, extractor works by successfully extracting assignment that make the circuit accept. Okay, now before we get into the actual working construction of PCD, which many of you may already seen before, I want to present first a very naive construction that works in some senses. So it's as simple as just concatenate the snark proofs. And in particular, the PCD prover is going to invoke the snark prover for the particular compliance predicate phi. And it takes in input for this node that we care about, the target node that's highlighted. And it just invokes the snark prover to give me a pi. And the final PCD proof pi that I construct for this node is going to be just as simple as the concatenation of all the previous proofs and the current proof. So this works because a simple analysis will tell us that this construction of the PCD is actually as secure as the underlying snarks, so exactly what we wanted. But the disadvantage is that there's no way we can keep this proof short, and in particular, the length of the proof grows linearly in the number of vertices we have in the computation. So the actual working construction is the recursive proof composition, in which the PCD prover and verifier invoke the snark proof and verifier for particular recursive circuit C. So recall that we said like a few slides ago, for this particular node, highlighted node, the blue one, we want to make sure that the proof pi is able to show us that first, the current computation is correct, and second, there is some valid proofs showing the correctness for the child vertices. So how do we capture this by circuit? The circuit takes as input all the necessary information associated with this node, and then it first checks whether the compliance predicate accepts for this particular node. And then it recursively invokes the snark verifier using the information about the child vertices. And if the snark verifier accepts, by definition, it means that there are valid proofs for the child vertices, which means that with high probability, the previous computations are correct. So the recursive circuit is just going to take the conjunction of all the decision bits and output one bit as the result. And with this magical construction of recursive circuit, we're able to very straightforwardly define the PCD interface, where the prover takes in all necessary information, invoke the snark prover about the recursive circuit, C, which is constructed, send the resulting proof pi to the verifier, where the verifier invoke the snark verifier, again for the recursive circuit C, and output a decision bit. But all previous works using this construction is only able to show that the knowledge soundness of the PCD grows exponentially with the depth of the transcript. In other words, there is no security when the number of depths of the recursion is larger than a constant. But in this work, what we show is significantly improved security bound for PCD based on snarks with straight line extraction. I'm going to go back to explain what is straight line extraction in a second. But the bound we get is essentially the ideal one we want. We show that the PCD is as secure as the underlying snarks, which matches with what people do in practice. And we don't, the knowledge soundness error of the PCD doesn't grow with the size or the depth of the transcript anymore. But the caveat is that in practice, snarks actually have non-black box knowledge soundness, and straight line extraction unfortunately only exists in idealized models like random oracle model. So why do we claim that our theorem is useful in practice? So what we do is that we actually propose a new idealization for hash-based PCD in the random oracle model. And since we're in the random oracle model, we have Michaelis snark, which actually has straight line extraction. Therefore, we can just directly invoke our theorem. And this actually provides the first justification for the current choice of security parameter that's used in practice, and especially for hash-based PCD such as Polygon and Sharp. Moreover, our work also has some theoretical implication. About 15 years ago, there's a work that constructs straight-line extractable snarks in the signed random oracle model, which is just a combination of a signature scheme and the random oracle model. What they show back then is that the notch soundness error of the PCD grows linearly with the size of the transcript. But using our theorem, we can remove this n factor. And we also get some improvement in the adversary running time. We have to keep track of the running time of adversary in this model because we use signature. And the similar thing happens with more recent work in the arithmetized random oracle model. So that's all I want to talk about. Thank you for listening.
So if the snarks are actually using the random oracle queries for the proof, how do you deal with that while recursively proving?
That is an excellent question. So how we deal with it, I think I have a slide on it. What we do is we actually use something called relativized succinct argument, where the language it handles is not just plain language, it's language that depends on the oracle. And we call this relativized snark. And in the random oracle model, actually a follow-up work by me and Ale, and actually a Bocconi master student, Annalisa, show that it is impossible to have both succinctness and relativization for snarks in the random oracle model. But in this work, our idealization kind of get around with this impossibility result by sacrificing succinctness. So that's the caveat.
Thank you.
Okay, I had a quick question. So in your, you said you model random oracle based, hash-based PCDs as some new idealized primitive called random oracle PCDs. So all of these PCD constructions that are based on random oracle snarks end up making non-black box use of the random oracle, right? So how do you model, or capture this fact that this random oracle PCD is making non-black box use of the random oracle itself?
So this is actually also handled by this notion of relativization combined with succinct argument. It's true that when you do recursion, you kind of have to take into account of the fact that you are using non-black box, you're using the snarks in a non-black box way. But fortunately, we know that for PCD construction, they actually only look at the hash function to check for correctness instead of actually destroy the hash function. So with our model of relativized succinct argument, we're able to kind of capture this fact that during recursion, you have non-black box usage.
Okay, thank you. Let's thank Zee again.